the coolest change of coordinates formula. So in this video, I'm going to show you a change of coordinates formula for n-dimensional spherical coordinate system. And I'm pretty sure you will love it. So let me first tell what the integral is. The integral is in the domain of this n-dimensional ball, right? Whose radius is capital R and the center of the ball is origin, right? This standard ball. And the integrand is 1 divided by this x1 square plus x2 square up to xn square, which would just be the radius square, right? Just like how in 2 dimension, like r square is x square plus y square. In 3 dimension, rho square is x square plus y square plus z square. Similarly, in n dimension as well, the radius would just be this x1 square, x2 square up to xn square, right? Yeah, so that's this 1 over radius square, and then this dx1 of dx2 of dxn is just the n-dimensional volume element, right? So this is also similar to how in 2D the dA is dx dy. Similarly in 3D dv is dx dy dz, so it's the same thing. Similarly over here the notation is this is n-dimensional ball because this is a subset in Rn, right? And it has radius capital R and the center is origin, so that's just a notation. And the reason I say ball here and not sphere is because if I say sphere, that could just mean the outer surface of a sphere, right? And if I say ball, it also means all the thing inside the sphere, the whole ball. Yeah, that's filled in. Yeah. Okay. So now how do we do this integral? So to do this integral, we would basically need to know how to change the coordinate, how to change this volume element while we are in a spherical system, right? Okay, so let's just go with 2 dimension, 3 dimension, 4 dimension first, and then I will gradually introduce you to how this dv in like dv sub n that changes like in n-dimensional spherical coordinate system. So I will just show you from 2D first. So in 2D, in normal like Cartesian coordinate system, we will just have x, y, right? So in that case, like our dA is just dx dy, right? But like we also have this polar coordinate system, which you can see as like the 2D spherical system, where you have this radius r, let's say, and here angle theta. So you have these two quantities to parameterize this whole circle, r and theta. And when r goes from 0 to capital R and theta goes from 0 to 2 pi, we get the whole circle, right? By using this, we can get any points in the circle, right? When r is going from like 0 to capital R and theta going from 0 to 2 pi, any points in the circle can be accessed by like this r and theta in this range. And the dA in this case, as you might know, is just r dr d theta, right? Yeah. Okay, now in 3D, when like in Cartesian where there are x, y, z, we know that the dv in this case is dx, dy, dz, right? In spherical coordinate system, we have three quantities. The first is radius, and then there's this azimuthal angle which goes from 0 to 2 pi, and then there's this inclination angle which goes from 0 to pi. So if you have to draw a figure, so there's a sphere like that, right? And basically this radius rho is basically some radius like that, right? The length from the center to any point on the ball. It could be inside the ball or maybe in surface anywhere, right? And this theta is, let's say, the projection of this line is over here. So the angle made from the x-axis, this is the angle theta, right? And the angle made from g-axis, this is the angle phi, right? Okay, so the projection of the line, and then after we project, the angle we have from x-axis, that's theta, and angle from g-axis is phi. So that's why phi is called the inclination angle, and this is the inclination angle, and theta is called azimuthal angle. Okay, so yeah, over here clearly we see that when this theta goes from 0 to this capital R radius r, the capital R is the basically the radius of the sphere, this r, and while theta goes from, so it has to like revolve around completely in this circle, right? So while theta goes like that from 0 to 2 pi, and the inclination angle can only go from 0 to pi. So in this, the values for rho, theta, and phi in this range can actually locate any point on the sphere, right? So yeah, so this is how spherical coordinate system work, and dv in this case is rho square sine phi, and then you can write d rho, d theta, d phi, right? Or you can also write in the opposite manner, d phi, d theta, d rho. Okay, yeah. So I think it's pretty clear till now. So now, okay, now how do we characterize the points in the and like the four-dimensional ball, right? Using spherical coordinate system in 4 dimension. So again, now in 4 dimension, like we would still have x, y. Let's write now x1, x2, x2, x3, x4, right? Now even here, like our dv would still be like dx1, dx2, dx3, dx4, right? And like two. Okay, now to get a like 4 dimensional sphere, the equation in like Cartesian coordinate system would just be that uh all the points satisfying this equation, right? Yeah, sorry, from r square, and like all of them being positive. So that would give us like 4 dimensional ball, right? And again, like so yeah, this is just the criteria for a ball. But again, to be able to access all the points, like we need to set up integral, which is really hard. But like over here, uh the way we do it is like we now have rho, theta, phi 1, phi 2, right? And yeah, it can be proved mathematically, which I'm not gonna go over the details. But like in the 4 dimensional ball case, our rho would still go from 0 to capital R, and theta would be going from 0 to 2 pi again. And there will now be two inclination angles, or like polar angles, you can call them. So this polar angles will just be going from 0 to pi, will just be going from 0 to pi, right? And in this case, our dv will be on rho cube sine square phi 1 sine of phi 2 d phi 1 d phi 2 d theta d rho. Okay, so this will be the db in 4 dimension, and this like these coordinates with the given like domain will be like enough to access any point on that 4 dimensional ball, right? And yeah, that's how we do it in 4 dimension. Now similarly in 5 dimension, there will now be like five coordinates, right? And this rho will now go from 0 to r, theta will be going from 0 to 2 pi, phi 1 will be going from 0 to pi, phi 2 will be, yeah, I know it's not really like you get visualizable, right? But yeah, there I mean, mathematically you will be able, you can verify that this actually gives like a certain 4 dimensional ball with has certain properties and things like that. So yeah, it's kind of like a theory thing. So, and this has like rho to the power 4 sine cube phi 1 sine square phi 2 sine phi 3 d phi 1 d phi 2 d phi 3 d theta d rho. Okay, I think you can see the pattern now, right? So this is for dv4, dv5. Now if you see the pattern, like for the nth dimension, like the dvn will be something like rho to the power n minus 1, and then a sine of n minus 2 phi 1, sine of n minus 3 phi 2. The last one will just be sine, but at this point there are like n minus 2 such azimuthal angles, right? Because there are n number of items, and so there are n minus 2 of such these things, right? So phi of n minus 2, and then d phi 1, d phi 2, up to d phi n minus 2, d theta, d rho. Okay, so now that you have this thing, you can also write it as a product in product notation from k equals to 1 to n minus 2, and sine of n minus 1 minus k, right? That gives n minus 2 Yeah, and then last is just 1. Yeah, okay, that works. And this is phi of k, and then d phi 1, d phi 2, up to d phi n minus 2, d theta d rho. Okay, now we know how this volume element changes in spherical coordinate system, right? And the limits will just be perfect. Like, so these are exactly the limits for a ball. So the limits of integration won't be that hard. Just this, the volume element will be a bit complicated, right? So that's the thing. So I think now we are good to go to the integral. So now we have that this is an integral in a ball of radius r with center 0 in n dimension, and the integrand is x1 square up to xn square, and there's this volume element dx1 up to dxn. So you already know that this will be an integral from 0 to r in rho, and then 0 to 2 pi in theta. All these phi's will just go from 0 to pi. This is 1 by rho square, and we know this thing will just be rho to the power n minus 1 sine to the power n minus 2 phi 1 up to sine of, let me write a few more terms for clarity, sine to the power n minus 3 phi 2 up to sine of phi n minus 2, and then there will be this d phi 1, d phi 2, so basically phi 1 for this, phi 2 for the next one, up to d phi n minus 2, sorry, uh, d phi n minus 2, and then d theta, and then d rho, right? Okay, now we can, using Fubini's theorem, we can do them just one by one, right? So from 0 to r, we have rho to the power n minus 3 d rho. The next integral, we have 0 to 2 pi of d theta. Next one, we have 0 to pi of sine to the power n minus 2 phi 1, right? And then for the next one, we have 0 to pi, sorry, so phi 1, and then d phi 1, I forgot d phi 1. So d phi 1, and then from 0 to pi sine to the power n minus 3 phi 2 of d phi 2, and then again from 0 to pi. I mean, it's the same thing, right? You can do this on your own, but let me write again one more. N minus 4 phi 3 d phi 3, right? And the last one will just be integral of sine of phi n minus 2 d phi n minus 2, and yeah, so that's it, right? Now the first two integrals are easy. Even the third one is easy if you actually can use the gamma function. Let me just write the formula over here. So this thing 0 to pi sine to the power, let's say some p of some phi d phi. This is going to be, first of all, this is twice the integral from 0 to pi over 2, right? Sine to the power p phi. Now let's write cos to the power 0 phi d phi. Now using the formula of the beta gamma function, this is half times beta of p plus 1 over 2 comma 0 plus 1 over 2, right? And this becomes beta of p plus 1 over 2 comma 1 over 2, which now becomes gamma function of p plus 1 over 2 gamma of half by gamma of p plus 2 over 2. So we can use this formula. And if we use this formula, now we will get, this being r to the power n minus 2 by n minus 2. Next is just 2 pi. And this will just be gamma of n minus 1 over 2, gamma of half by gamma of n over 2. Next one, gamma of n minus 2 over 2, gamma of half by gamma of n minus 1 over 2. Next one, gamma of n minus 3 over 2, gamma of half by gamma of n minus 2 over 2. Next one, and so on. The last one, gamma of 1 plus 1 over 2, gamma of 1 over 2 by gamma of 3 over 2. Yeah? Okay. So now, yeah, so this is it, right? So now notice that there's a pretty good cancellation. Cancellation. Definitely, this will also cancel. This will also cancel, right? Yeah. So now what remains is that there is this thing. Okay, so r to the power n minus 2 by n minus 2 into 2 pi. Now there are these n minus 2 of such gamma 1 over 2. There's gamma n over 2 and gamma of 1, which is just 1. So I can write this as r to the power n minus 2 by n minus 2 into 2 pi. Gamma of half is root pi, so pi to the power n minus 2 by 2, and then gamma of n over 2. So now there's that pi which can multiply with the pi. So this becomes 2 into, that just becomes pi to the power n over 2 by gamma of n over 2. And that's our answer, right? So this is our answer. So basically 2 pi to the power n over 2 by gamma of n over 2 times r to the power n minus 2 by n minus 2. Yeah? So let's say if this matches or not. Yeah, 2 pi to the power n over 2 by gamma of n over 2 r to the power minus 1. Yeah, that exactly matches. But like I wanna show you something more. Yeah, so this was actually a pretty good application of this spherical coordinate system in n dimension, right? And I think you enjoyed this video, even though I made it pretty long, which wasn't really necessary. But I have something more to give you. So you see, there's this thing. This is not really anything random. Like this is actually a quite useful term, right? And there's also a reason why this is here. If you had solved this integral a different way, there's also another way, I mean, where you can use some surface area things, right? And then that could have been an easier approach, but I just decided to go with this to demonstrate the n-dimensional spherical coordinate volume element, right? But yeah, let's talk about this expression. So there's actually a formula for n-dimensional volume and n-dimensional surface area. Even though I denote this as Sn minus 1 because the dimension of the surface area is n minus 1, right? Because like for 3D is like ball, the surface area is 2D, right? I mean you can look at any point on that like surface by using just like this theta and phi, right? You don't need r because r is just capital R. So there just need two things. So that's why that surface is two-dimensional, even though the ball is three-dimensional. So that's what I mean. So that's why even though this is a surface area of n-dimensional ball, we give n minus 1 as its subscript, and this is volume of n-dimensional ball. Okay, volume of n-dimensional ball. Okay, now there are the formulas for it, and yeah, they have pretty good revelation as well as the connection. So this one is just 2 pi to the power n over 2 by gamma of n over 2, which is the exact same expression with r to the power n minus 1. And this one is pi to the power n over 2 by gamma of n over 2 plus 1 r to the power n. So I think this is pretty cool because this is the same thing. And let's see, and even while we try to find this volume, and like for like one dimension, like you get pretty good insights about what actually is surface area, like so let's go with 3 dimension first because we know that formulas, right? And we'll go to 2, we'll go to 1, and we will see some insights that you might not have known earlier. Okay, for 3 dimension with 3 of r, this is just pi to the power 3 half by gamma of 3 half plus 1, which is 5 half r cube, right? And this becomes pi to the power 3 half by, that's 3 over 2 into 1 over 2 into root pi r cube. So this is just 4 over 3 and that's just pi r cube. Yeah, and that's the answer, right? Okay, so that works. Now if you try to find b2, that's just pi by gamma of 2 by r square, which is just pi r square, and that works, right? So now notice that the two-dimensional volume, okay, so here notice that 3D volume is just volume, right? Yeah. Now 2D volume over here is area. So what do you think is 1D volume? What do you think is 1D volume? Huh? It should be length, right, according to our perspective, and that's exactly what the formula will give. If you try to find v1 of r, that will just be pi to the power, so it's just like with the radius r, right? So pi to the power half by gamma of, this is 3 half by r, and now this is pi to the power half by half times root pi r, and that's 2r. Exactly like a sphere with a radius r, like in one day, this line will just be extended to other side as well to form a sphere, right? And its length is just 2r, right? So see, like these formulas actually give us new intuition on like how 1D sphere should be, right? So this radius extended in both sides and this length is just 2r, and that's what the formula gives. And you can even check that for 0D. Like what do you think for 0 dimension? For me, it should be the count, right? The count of the number of points. So like this length, when extended in 2D, that becomes area. In 3D, that becomes like volume. In 0D, that's the count of the number of points. And that should be 1, right? Just 1, yeah? Because this one, just 1 point. I mean, it's in 0D, so there's just 1 point. So 0D volume should be 1. And if you try to find that, so it's pi to the power 0 by gamma of 1 by r to the power 0. And it has no units. So that's just 1, and that exactly works. And yeah, not just volume, even the surface area will give you pretty good insights. Okay, so let's say our 3D surface area is just surface area, right? Yeah. So basically, okay, so let's find this. So 2 pi to the power 3 half by gamma of 3 half r square. Now 2 pi to the power 3 half, this is half times square root pi r square, so that's 4 pi r square, and that works, right? So this is the surface area of a sphere, right? Now what should be 2D surface area? 2D surface area like will be the perimeter length, right? The perimeter of circle, right? The circumference. So the perimeter length. So it's length right now. So circumference, that's right. Okay, of a circle, right? So now if you try to find it will just be 2 pi r. Like, so S1 of r will just be 2 pi by gamma of, that will just be 1 and r. So that's just 2 pi r. Exactly. Like the formula knows that the total surface area which should be the circumference of a circle, right? And now what would be 1D surface area? Like that means for a line, the 1D volume was length, right? Now what would be 1D surface area? Okay, so now like the surface area is actually about the boundaries, right? Like for circle, like we had the boundaries length. For sphere, we had like boundaries area. Now for line, in boundary there are just like this. There are just like the endpoints, right? In a line, there are just this endpoints, right? So there are like two endpoints. So we know that from the previous intuition that it should be count, right? Like the count of the boundary points, like count of boundary points. And there are two boundary points, right? So the one surface area, it should be two, just no units, just count, right? So and if you use the formula for like 1D surface area, that will be exactly 2. So if you want to check that, so 2 pi to the power, yeah, so you need to, okay, if you want to, okay, so over here, n is 1, right? So pi to the power 1 by gamma of half r to the power 0. And here it was 2 over 2, okay? Just for information, because here it was 2 over 2. Let me write that properly. And yeah, so this is just 2, okay, wait, here it's half. Okay, so 2 root pi by root pi, and r to the power 0 is 1. So it's exactly 2, just a number, just the count of boundary points. And that's 1 surface area. So there are all these new insights you get from these formulas. And I think this is pretty cool. What do you say, guys? So yeah, so now you have all these insights about like count, length, area, volume, and so on. So sometimes if you are able to generalize formula, you can actually get pretty new and deep insights, and that's the beauty of maths, guys. I think like this person was more beautiful than the actual solution, and I do hope you guys enjoyed it. I think I should actually cut this person and make a new video out of it. So yeah, anyways, thanks for watching. So yeah, that's definitely helpful if you watch for long. Like you get this beautiful insights, right? So yeah, look forward to seeing you in the upcoming videos too.